Hi. Well, today we're going to talk about exponential functions. And as you can see here, there's two different kinds of exponential functions. There's exponential growth and exponential decay. Okay, and first of all, what I have here is a graph. Well, the equation of an exponential function is y equals a times b to the x power. And if you look carefully here, the little x is up there as an exponent. Okay, and the two numbers before it. Okay, looking at the graphs of exponential growth and decay, exponential growth means get bigger, and obviously you can see it gets bigger. It's a curve. It's not a linear function, not a straight line anymore, not a U, not a parabola, okay, but it's this curve. Okay? And exponential decay starts out big and gets smaller. And you notice they kind of level off. In this particular case, they both level off at 0. There's a special name for the line or the number that it levels off at. It's called an asymptote. That means it gets really, really, really close to it, but never touches it. Okay? And in this particular case, they're both at 0. This is what's called the parent function. Okay? And looking at a couple other things about these, the domain and the range. If you remember, the domain is all the x values of a graph, of a function. And that talks about how far left or right the graph goes. Well, if I look at my exponential growth function, it goes to the left forever. Okay? And it's going up, but it still continues to go off to the right. It never gets perfectly vertical. So it does continue to go to the right forever as well. So it's left forever, right forever, and everything in between. The x can be anything. It can be all real numbers. Okay, the range describes how high or low the graph goes. Okay, well, obviously this one goes up forever, but does it go down forever? No. It levels off of that asymptote of 0. And that's how I got y is greater than 0. It gets really close to 0, but never touches it. And notice it's not greater than or equal to. There's no line underneath that. It's just greater than 0. Okay. And one last thing here, down here at the bottom of this equation, there's a way to tell if it's growth or decay by just looking at the equation of the function. And we're going to look at that letter b. Okay. If b is greater than 1, then it is an exponential growth function. Okay? So you can always graph it, but you can certainly tell by the equation, as we'll see here in a minute as well. With exponential decay, same type of thing. You notice this graph, it starts out high and gets lower. It levels off at 0. But describing its domain and range, the domain, it goes to the right forever. It's going up and to the left forever. So again, the domain is all real numbers. The range, how high or low, what's going up forever. But notice here again, it levels off at 0, so it's just greater than 0. And again, there's a way to tell if the graph is growth or decay by looking at its equation. Okay? And in this case, if b is less than 1, then it's going to be exponential decay. Okay? But it's the letter b that we want to take a look at that's going to help us determine that. Okay? So again, these are what are called the parent functions, kind of the general, plain Jane generic equations of these exponential functions. Okay, let's take a look at the next one here. It's another little kind of the book's definition of exponential functions. They give one here, y equals a times b to the x. A couple little examples here. Okay, notice this one right here doesn't have a number in front. Okay, this is really y equals 1 times 4 to the x. It doesn't have an a. That's okay if it doesn't have an a. Same thing with this one. It's y equals 1 times 1/2 to the x. Okay. And this one obviously has an a and a b. Okay. All right, on the next slide here, the first thing we're going to do is we're going to take a look and determine if these things are exponential growth or decay. Okay, and we're going to look at the letter b. And if you look closely at that one, letter b, the b is 3. 3 is greater than 1, so it's exponential growth. Okay. Here's the b again. There's no a, it's 1. That one's exponential growth as well because the 4 is bigger than 1. But when I look at number 3 now, look carefully at number 3. Scooch this up a smidge. When I look at number 3 here, the letter b is 1/2. 1/2 is less than 1. This one would represent exponential decay. And oftentimes people say, well, if that b is a decimal, or if it's a fraction, oftentimes they think, well, if it's a fraction, it's automatically decay. Hey, well, a lot of times it is. But look at this guy right here. 5/2, it's a fraction. But is that fraction less than 1? No, 5/2 is actually 2.5 or 2.5, which is bigger than 1, which makes this one be exponential growth as well. Okay? So again, we can look at the equations of the graphs to determine if it's exponential growth or decay. Okay. All right, the next thing we're going to take a look at is we're actually going to take a look at graphing some of these. Okay, and these are some different things that we're going to do when we graph these. Okay, and this is where your graphing calculator is going to come in really handy in helping us make these graphs. So I'm going to put an equation up here, and let's start with this one. Y equals 2 to the x power. Okay, now technically, that's y equals 1 times 2 to the x power. It doesn't have an a on it, which is perfectly fine. Okay, and I'm going to try and answer these questions right over here. I'm going to erase this real quick. Let's try and answer these questions. Is this equation exponential growth or is it exponential decay? Well, this is b. b is bigger than 1, so this is going to be exponential growth. Okay? All right, well, to graph this thing, ultimately what I'm going to want to get is a graph. Okay, I'm going to grab my graphing calculator here and turn this on, and we can hopefully look at it here. Okay. And I'm going to type that in my y equals, and I'm going to go 2 raised to the x power. And if I press graph, it's going to look something like that. And yep, sure enough, it certainly does look like exponential growth. Okay. Now, number 2 over here says, use the calculator to find some points. Okay, well, rather than picking our own points and making our own table of values, does the calculator have a table built in it? Yes, it does. And I think we've worked with this before. If on my calculator, if I press second graph, it goes to my table. Okay? And if I look carefully here, okay, there are a bunch of nice points.
Danielle, please call
okay, this one doesn't look too terribly bad. Okay? Now, I'm not going to make you copy down these points. Okay? I'll make a little sketch over here. And you guys have graph paper, hopefully. But can I graph some of these? I can do 0, 1. I can go over 1 up 2. Okay, over 2 up 4. Over 3 up 8. It just keeps getting bigger and bigger and bigger. You can kind of see it makes a curve. Okay. Make sure that when you graph these that I can see those points really nicely, kind of exaggerate them a little bit. But it's also nice if I could see something over here. What happens when these x values get smaller? Okay, well, look at x is -1. I'm going to go right here. Okay, -1 is 0.5. So left 1, I only go up a half. If I go up a little bit more here, -2 is only up 1/4. It's getting smaller and smaller and smaller. And if I keep going up here, you can tell that these decimals over here, they get smaller and smaller and smaller, and they're getting closer and closer and closer to 0. Okay, so when I make this curve, I'm going to come down, and I'm going to get close to 0, but I'm going to try not to touch 0. Okay, and that's going to be a picture of our exponential growth. Okay, we're going to let the calculator find points for us. Sometimes there will be a couple nice points, 3 or 4. Sometimes there's only going to be 1 or 2 nice points. Okay, it's okay, and you're probably going to have to graph some decimals sometimes. Look for nice ones, like ones that are close to 0.25, 0.5, 0.75. But find those nice ones. Okay, when you graph these, I'm going to ask you to be a little neat with your graphs. Okay, you should make a nice curve, as you can see on here. And sometimes it gets to be a little bit hard to show the points over here and over here as they get really small. Okay? But I'm going to be a little bit picky when you guys turn in your homework. Don't do this, and it doesn't go past the axis. Okay? It doesn't go down and then come back up again. It doesn't do that either. Okay? It should come down and then level off at 0. And once you get really close to 0 there, you can kind of stop. Some people, I see this, where they kind of extend it out. No need to go that far. Okay? Just get down to the axis, get fairly close, put a little arrow on the end. Okay? And like I said before, make sure I can see a few of these points. Okay? And that you just don't have a graph with a curve on it. I need to see points. And we've talked about this in the past as well. Okay? So that's number 2, how I would make a graph. How about number 3, the y-intercept? How about this guy? Okay? Well, if you remember, the y-intercept is the point where the graph crosses the y-axis. Okay, we can see it right here. Okay, and if you remember anything about the y-intercept, okay, anything about its coordinates, the x-coordinate is 0. Okay, well, where in my calculator can I go to find the y value when x is 0? the table is a great spot to do that. If I go second graph and go back to my table, and when I scroll down here and find when the x value is 0, it tells me my y-intercept on this one is 1. Okay? And if you wanted to, you could write 0, 1 if you wanted to. Okay? The domain. Okay? Well, the domain on all of these exponential functions is all real numbers. The range, and notice with domain how I always write the letter x. The range is the y values. Let's talk about how high or low did it go. If I go back to my graph over here, it's a little bit neater. It goes up forever, but again, it levels off at 0, and it's everything above 0. So all the y values are greater than 0. Okay? End behavior. Okay, I think we saw this once upon a time. The end behavior talks about at the end of the graphs, out at the edge. That's talking about like over here and up here. Okay? As x gets bigger, this means as I go to the right on the graph, as I go to the right, where does it eventually go? It goes up. And when it goes up, what's happening to the y values? The y value is also getting bigger. Okay, we can kind of just keep it simple like that. And the very bottom one over there, it says as x gets smaller, that means as I go to the left on the graph, okay, where's this one going? Yep, it's getting smaller, but is it getting smaller and smaller and smaller forever? No, it's approaching 0. Okay, and I could say y gets close to 0. We kind of keep it just simple like that. Okay, so when we graph these things, they're going to ask you to identify several of those things, specifically the y-intercept, the domain, and the range. Okay, but there's one little example. Okay, we're going to try another one here once. Okay, and again, I think having a graphing calculator is going to be really helpful. Having graph paper, whether you print it off or you go get some, either one's okay. We're going to try this one. Y equals 1/4 to the x power. Okay, well, can we answer that question? Is it growth or decay? Well, if I look carefully at the letter B here, B is less than 1. 1/4 is less than 1, so this one's going to be exponential decay. And eventually, this graph should go down. Okay, well, let's grab my calculator. And remember, when I go type these in, fractions always have to be in parentheses, so I'm going to type in 1 divided by 4 raised to the x power. And if I press graph, sure enough, it gets smaller, it goes down. Okay. When I graph this, then we need to graph some points. Okay, so on your graph paper, you're going to see a little axis. If I go back to my table, okay, now these numbers are really big, but how about -1, 4? That could be on there. 0, 1, so something like -1, 4, 0, 1. Then I get over 1 up a 4th, and you can kind of see how they get really small in a hurry. Okay. As I go down my table here, the numbers are getting closer and closer and closer to 0. Okay, so this one had a couple nice points. Okay, but don't be afraid to graph the decimals as well. Okay. How about my y-intercept? Again, we said the y-intercept is the value of y when x is 0. Well, if I go to my table, when x is 0, y is 1 again. It happens to be the same as the last one. Okay. My domain, the x values, it's all real numbers. Left forever, right forever, everything in between. The y values, this one comes down and levels off at 0. And the graph is everything above 0. It's not equal to, it's just greater than 0. And end behavior, as x gets bigger, let me go back to this one for a second. As x gets bigger, as I go here to the right, what's happening to the y values? The y values are getting smaller, but specifically what number are they getting close to? 0. Okay. Y gets close to 0. And as x gets smaller, that means as I go to the left on the graph, as I go to the left, it's going up, 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 and the y values are getting bigger. Okay. So there's an exponential decay one. Okay. I got one last one we're going to try, and it's a little bit different. Okay. But as we'll see here, here's my last one that I'd like to try. What if I had this? Y equals 1/2 times 3 to the x power plus 2. Okay, oh wow. That equation looks a little bit fancier. There's a couple different things on there. Okay, I have an A now, and then I have this thing out here at the end. Okay, but there's my B. Could I decide is it growth or decay? Well, there's my B. It's the number that's being raised to the power. B is greater than 1, so it's going to be exponential growth. So it should go up. Okay, let's try graphing this on the calculator. Now be careful, it's a little bit trickier. I see 1/2, so I got to put in parentheses, times 3 raised to the x power. And you guys with the new calculators now, I want this plus 2 to come at the end. Okay, you guys with the new calculators have to press your right arrow so it comes off the exponent and comes back down. Okay, and we write the plus 2 out there at the end. Let's see what this does to the graph. Oh, look at that. Okay. If you look closely, it doesn't level off at 0 anymore, does it? It levels off at 2. Yeah, and this little number out here at the end bumped it up 2. If it was a minus 2, it'd be down 2. Okay, down 2. But anyway, if I went to my table, okay, do we have some points here? Ooh, I don't see very many nice points. When I go here, it gets to be really big. There's a couple decimals in here, some 0.5s, which should be okay. Okay, we might have to graph the decimal ones. Okay. And I'm not going to take the time to do this because I think you can do it. Over 0 up 2.5, over 1 up 3.5, over 2 up 6.5. Okay. And if I go up here, if you look closely, as I go to the left, these y values or x values are getting smaller. You notice the y values are getting really, really close to 2, aren't they? They're getting smaller and smaller and smaller. Okay. But in the end, we should get a graph that looks something like that. Okay. Does it have a y-intercept? I'm looking at number 3 over there. When x is 0, scroll back down here. When x is 0, what's my y-intercept this time? 2.5. 0, 2.5, right here. Okay. The domain, I'll go back to my graph because to me it's easier to see when it's a picture. Does it still go to the left forever? Is it going up and is it going to the right forever and everything in between? The domain is always all real numbers. It's going to continue to be all real numbers, I should say. X equal all real numbers. The range, okay, it's going up forever, but it doesn't go down forever. Okay, and we talked earlier, just a minute ago, it's leveling off at 2. So all the y values are above 2. Another way of saying that is all the y values are greater than 2 this time, not 0, but 2. And end behavior, as x gets bigger, again, this means as I go to the right on the graph, as I go to the right, the y values are going up. They're getting bigger. And as x gets smaller, as I go to the left on the graph, that's over here, they're getting smaller and they're leveling off and getting really, really close to 2. But if it's everything above 2, y gets close to 2 this time. Okay. So that's kind of the main focus today is graphing these exponential functions and identifying several of these things right here. Okay. Like a calculator is going to be really, really helpful. Okay. All right. One of the last things we're going to talk about is what if they give us a table of data? Okay. And can we determine from the table, without graphing again, whether it's exponential growth or if it's exponential decay? Okay, or for that matter, whether it's just an exponential function altogether. In order to be an exponential function, there's a little pattern with the y values. Okay? In order to be exponential, the y values have to multiply by something every time. Okay? This has to be a positive multiplier. So every time when you go, maybe it's times 2, times 2, times 2, times 2, times 2. But it has to be the same everywhere across. Okay, but it's a multiplier. When we talked about linear functions a while back, the y values they were adding by 2 every time, or subtracting by 2 every time. Okay, it was going up and over, up and over, up and over. Okay, but it was adding or subtracting. But here, with an exponential function, it's a multiplier. Okay? All right, we're going to take a look at a couple here and determine, is this exponential? Okay, I'm going to look at my y values. What's happening as I go from one to the next to the next? Okay? If I want to find out what it's multiplying by, I can take the second number and divide it by the one before it. So 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. 2 and 2. I know a lot of you guys can just see that it's times by 2, but if you can't, you can always do a little division problem. Okay. Yep, it was multiplied by 2 every time. This is, yes, it is exponential. Okay. Yep, got it. Okay, how about this guy? Ooh. Things are getting smaller. And by the way, let me back up 1 second. This would represent exponential growth. And one way to tell it is because this multiplier is a number bigger than 1. And then also, you can tell the numbers are getting bigger. And if you were to graph them, it's going to look something like this. Okay. Let's skip ahead to the next one here. If you look carefully at the y values are getting smaller. But are they going down by the same multiplier? And there's a couple different ways to think about this. Some of you guys, from 100 to 50, some people are thinking divide by 2. 50 to 25 is divide by 2, divide by 2, divide by 2. They're going to be cut in half. Okay, but when we talk about this exponential thing, eventually we're going to need to know what is the multiplier. Well, dividing by 2 is the same as timesing by the reciprocal, or timesing by 1/2. 100 times a half is 50. 50 times 1/2 is 25. Times a half times a half. Okay. But my point is, it is a multiplier. It's the same multiplier all the way across. So yes, this is also an exponential function. And because the numbers are getting smaller, and more specifically, this is like our b, the multiplier is the number less than 1. Oops. This is actually going to be exponential decay. Okay, good. Here's one last one. How about this? If I look at my y values, getting smaller, so are we divided by something? No. Okay, and I think a lot of you can see this. I think the rule here is they're subtracting 5. It's minus 5, minus 5, minus 5, minus 5. Well, do exponential functions have addition or subtraction? No, it has to be a multiplier. So this one is not an exponential function. Okay, not exponential. Okay. So you're going to see a few problems that look like this as well. Determine whether or not it's exponential or not. Okay, and this is the very last one. Okay, can we use an exponential equation to find the value of something? Okay, you buy a brand new car for $25,000, the value of the car depreciates, okay, as soon as you drive it off the lot. Okay, if you know anything about the word depreciate, depreciate means the value of the car goes down. Okay? The value of the car after T years can be modeled by this equation. Okay? So this right here is the original cost of the car, a $25,000 car. Okay? And it has 82% of its value every year that you own it. How much would it be worth in 5 years? Well, we're just going to take this 5 and we're going to plug it into the equation right there. Okay, if I use my calculator, see this still? If I take 25,000, okay, and I times it by 0.82 raised to the 5th power, after 5 years, that car is worth $9,268. And that'd be 50 cents if I round it with money. Remember, money goes 2 places. That 6 is going to make the 49 round to a 50. Okay. So in 5 short years, it's worth almost only 1/3 of what you paid for it. Okay. This is kind of interesting. I'm going to go back here just for 1 second. I'm going to graph 25,000 times 0.82 raised to the x power. Okay. And I won't be able to see my graph, but I'm going to go to my table. Just look at this really quick. This is kind of interesting. So in year 0, I'm going to scooch up here to the bottom. In year 0, my car was brand new. At 0 years old, it was worth $25,000. Every year, you can see the first one. After 1 year, it's only worth $20,500. Went down $4,500, and then it went down more and more and more and more over here. Okay? And there's our 5 years. What we did over there at the screen. How about if it's 10 years old? That's only worth $3,436.20. Okay? Yeah, kind of interesting. Okay, it depreciated really, really fast. It lost $4,500 the first year. Okay, but the amount that it's going down every year after that is getting smaller. It's kind of leveling off. Okay, yeah, kind of interesting. So at any rate, once again, 2 different things we talked about today: exponential growth functions and exponential decay functions. We worked on graphing them, finding the points, finding the intercepts, talking about the domain and the range, and then looking at some problems where they're given the table to determine if it was growth or decay. Okay, all right. Good luck. Thanks for tuning in.